Człowiek. 전화번호 없나?
Amazon customer service. I'm here to help you, first by finding your account, then by asking you a few questions to get the right help. Just so you know, this call may be recorded to provide you with the best support. To continue, we need to confirm your account. We can send you a text message with a link to do this. Message and data rates may apply. Press 1 if it's okay to send you a text message now. Otherwise, press pound. We've sent you a text message. When you get it, open the link to continue. I'm sorry, we weren't able to verify your account. I've checked your account, and it looks like your monthly Prime membership renewed on January 26th. You were charged $12.99. Do you need help with this charge?
Yes.
I've checked your account, and it looks like your monthly Prime membership renewed on January 26th. You were charged $12.99. Do you need help with this charge?
Yes.
Okay, I can help you manage your Prime account settings, or I can help you cancel your membership on the call. Which do you want? You can say things like account settings or cancel Prime.
Cancel Prime.
Sure, I can cancel your Prime membership for you. You'll get a full refund of $12.99. Should I cancel your membership now?
Yes.
Okay, I've refunded you $12.99 and canceled your Prime membership. Your Prime status will take a few minutes to be updated on your account, and your refund will be processed within 5 business days.
Okay.
Would you like me to send you a text message confirming your cancellation?
Yes.
Sorry, I couldn't send you the text message. But rest assured, I have canceled your Prime membership while I'm on the line. Is there something else I could help you with?
No thanks.
Now, I'd like to know how I can help you. You can take your time and talk to me, just like you would with a person, and I'll ask questions if I don't get it. So, tell me, why are you calling today?
I'm done.
Just a moment. An associate will join you shortly.
Okay, I bring the camera in line or aligned with my position so that you can see me better. Let's wait a few more minutes before we begin. As we are waiting, are there any questions or any suggestions on how we can improve the online course? Or any questions that you have? Anybody?
I have a question. Do we just email you our homework? Or does
No, please go to Brightspace and in your homework. Do you know how to do that? I haven't done that myself, but I think one of our TAs should be able to do that, especially Ivan Omatowski.
Okay. I just didn't, maybe I haven't checked in the past few days. I didn't see somewhere to submit it.
I didn't see a submission link either.
I'm looking at it now, and there's a spot to upload.
Perfect. Okay.
Maybe it's happened in the last 12 hours then.
Yeah, so I haven't done that myself, but some of the students were in my course previously, but then they kept changing the system. We were using Blackboard for a while, but now we are switching to Brightspace. So the way of handing in homework may be slightly different, depending on if you're doing Brightspace or Blackboard. Okay, I think it's time so we can get started. Before we get started, are there any questions? If not, let me share my screen. It's not what I want, and this is my slide. And okay, can you see my screen?
Yes, we can see your screen.
Okay, wonderful. Let's get started then. The last time we were talking about electrostatics, and this lecture, I like to talk about magnetostatics and boundary conditions, which are also known as jump conditions. So we start with magnetostatics first, okay? And before we begin, I like to just regurgitate what we have learned in the last lecture on electrostatics. So what we have learned is that in statics, which is a simpler form of, let me see, this doesn't write. Maybe this would write. Let me see, things are not writing. Let me see, where do I switch to? To the writing mode. Does anybody know where I can switch to? Maybe this is it. And if I go back there and share my screen, well, that is not it. Apparently, it's not the way. Well, the PPT slide is not writing. So does anybody know how I can switch from the presentation mode so that I can start writing? I'm usually pretty bad at this kind of thing. Well, let me see if it writes now. Still doesn't write. Somehow there's a way to switch from, maybe this does it. It doesn't do it.
I think you have to click on the pen. Right now you're on select objects. There's a pen on the very left. Like right under files, there's a pen option.
The pen doesn't read. Click a file. What do you say again, please?
Like there's a pen option, like right under the file.
There's a lot of pen options here.
No, like, yeah, click on the one icon that's right under files. No, not file, but the.
Let me see, I have ink that gives me all this. This
Yeah,
one?
click on that.
Let me see if it writes now. Still doesn't write. Instead, they try to draw a picture for me. I'm at the lost.
Because it's still on select objects, somehow the pen thing is not like highlighted, I guess.
Yeah, you are correct. I'm still on selecting objects. And how do I get out of this mode?
I think you would better restart the PowerPoint.
Yeah.
Something's going wrong here.
Okay, I think I just did that. Let me try it again. Okay, let me try.
Maybe just open up a blank one.
Let me see if I go to ink. I still cannot write on this PowerPoint. Let me see if I just open up a blank one. And if I have a blank presentation, let me see if I can write on it. It still is in that select mode. I don't know how to get rid of that. Usually I do a very stupid thing, which is to reboot my computer. Does anybody have any suggestions other than me rebooting the computer?
So you can add the draw tab. So if you go up and add the draw tab to your ribbon. So
Where's the draw tab? I'm in the PowerPoint now. Can you see my screen?
yeah, if you can let me share my screen, I can show you how to do it.
Okay, let me see. Very good. I can go to View Share. I can also go to, let me see.
I can also just try to talk you through it. So if you click one of the other tabs on your PowerPoint, like View.
Yeah, here's my PPT, I think. Let me open up the old one again. The PowerPoint that I want to use is this one for today. I go to View, and then what do I do here?
So then you'll right click in the open space on the top right of your toolbar. Yeah, right there.
Okay.
And then hit Customize the ribbon.
Okay.
And then there'll be you see the empty checkbox on the right side that says Draw?
Empty checkbox on the
So
right
there's
side.
a list of a bunch of stuff on the right. It's the second one on the list. It says Draw.
Draw, okay.
So check that, then hit OK.
Okay. Hit OK.
Okay. Then now you have Draw on the top. So now at the top left, you have Home, Insert, Draw. So click Draw, and then click the black pen.
This one.
Yeah. And I think.
Okay. Good. Thank you. Thank you. Who is this person who helped me out just now?
This is Michael Williams.
Or Michael Williams. Can you email me the instruction just in case I get stuck again in the future?
Yeah, I can do that after class.
Yeah, after the class, you can email me the instruction, because these kind of things always confound me, because it works sometimes and it works differently depending on your initial condition. Okay, I think this is the slide I want to share. Okay, so sorry for the delay. So I'm actually going to talk about magnetostatics today. And in the last lecture, we talked about electrostatics, where we actually convert Maxwell's equations by solving only the electrostatic problems. But then for magnetostatics, then we have these two equations to solve, which is Ampere's law. And then I have the Gauss law. And these two equations have to be solved in tandem, because solving this equation alone is not enough. And even though there are three scalar equations and three unknowns, you cannot solve for H by solving this equation, and J is usually known. Okay, J is assumed known. J is like the input to the system. Okay, so the way to solve this problem using the wisdom of our predecessor is to let B to be curl of A. B is curl of A because if you do this, then using the fact that divergence of curl of A is always equal to 0, because the diff of a curl is always 0, as I said before. This is the same identity as that A dot A cross B is always equal to 0, because A cross B is always orthogonal to A. And if you dot it again with A, it always gives you 0. And you can prove this identity by going through a lot of linear algebra, or hence algebra. And you can use the same algebra to prove the identity above. So having said this, how do we solve this problem? Well, I have to remind you that we have proved that this dial operator can be written as this form, where x hat, y hat, and z hat are unit vectors in this course. Okay, and then if we do that, then what we have is that using the constitutive relationship that B equals mu H, it implies that H is 1 over mu curl of A. And if we use this relationship and so on, we have this as our relationship. And then plugging this definition of H into Ampere's law, we get the fact that curl of 1 over mu curl of A is equal to J. Okay, then the equation somewhat simplifies, but still not solvable. I will not discuss the reason why it is not solvable right now, but we have to simplify it further. And one way to simplify it further is to assume that mu is a constant, which is true for free space or vacuum. For instance, mu equal to mu naught for vacuum. And then mu is a constant that can be taken out of this divergence or gradient operator or the del cross operator, and I can take mu to the other side, and then the equation simplifies somewhat by taking mu to the other side. And it's still not simple enough for us to solve this equation. To solve it, we have to use vector identities to reduce this curl of curl. This usually implies this, but in most textbooks would not bother to put the parentheses around the second curl. When you have a double curl operator, there is an implied parenthesis around the second curl. And we use the back of the cap formula again to simplify this equation. Okay, and the back of the cap formula, if you remember, A cross B cross C is equal to B A dot C, this is the back, and then C A dot B. Okay, so using this formula for this double curl operator, bearing in mind that this is algebra, you can prove it using algebra, but now you have to be mindful of the fact that the del operator is a differential operator, and when you apply this, you have to make sure that the order is very important. The thing that the del operator operates on is always to the right of this thing, and if you keep that in mind, then you will have this double curl is actually equal to this thing, equal to mu J. And we are going to make one more assumption or one more condition to simplify this equation. We are going to require the fact that divergence of A equal to 0. This is called the Coulomb gauge. And if that is the case, then this equation that we have is just minus the Laplacian of A equals mu J, or plus Laplacian of A is minus mu J. Okay, so this greatly simplifies the equation. And it turns out that this equation is solvable. I do not want to explain in detail why it is solvable, whereas previously it was not solvable, because we have found solution to an equation that is very similar to this. And if you have a Laplacian of A, and this is the scalar, and if you write in gory detail, it will be just like Laplacian of components of A written in this manner. And that then when you do this, you can notice that the Laplacian, which is combination of derivative operator, commute with this unit vector, which is a constant. So you can also rewrite this as x Laplacian of AX plus y Laplacian of AY plus z hat Laplacian of AZ. And this is called commutation, and that is equal to minus mu J. Hence, you can write this equation as three different components, or with the three different components that Laplacian of AX is just mu JX. If I pick out the X component of this equation, then of course you can pick out the Y component and the Z component, and you get 3 equations. But each of these equations looks very much like the Poisson's equation that you have studied in the last lecture. I hope you're reading your lecture note as well. Okay, the Poisson's equation was this equation. And we have learned how to solve that equation. We say to solve that equation, we first find the point source response, that what happens if the charge density is equal to a point source like a Q delta R minus R prime. And if that is a point source thing, and if you put this back into this equation, and then you have something called the Green's function, which is a solution to a point source response. So if I define the Green's function to be this equation, and we know how to solve Poisson's equation when we have a point source, we just invoke Coulomb's law, because we know that such a potential is proportional to something like R minus R prime. And hence we conclude that a Green's function is actually minus 1 over 4 pi R minus R prime. So using some sort of a clever trick, we find a solution to the Green's function equation. Okay, this is the Green's function equation. Okay, and then we can use the idea of linear superposition, because if you know the point source response to this equation, when the right-hand side is a distributed source, and if it's a point source, you can use the principle of linear superposition to claim that any distributed source that I have, which is a function of R, can be written as a linear superposition of point sources. This is just a mathematical statement. You can convince yourself that this is true. But dr prime here means the x prime, the y prime, the z prime. And delta function here is a shorthand notation for delta x, delta y, delta z. And using the property of the shifting property of delta function, you can convince yourself of this equality over here. But this equality is just a physical statement that any sources that you have can be written as a linear superposition of point sources. If you think about it, meditate on it, this is what this statement says. So if you have a linear system, okay, and if this right-hand side can be written as a linear superposition of point sources, and you know how to find the point source response to this, and we learned that in electrical engineering, if you know the impulse response of a system, the arbitrary time response will be given by the convolution of the input with the point source response, which is the impulse function. But in this course, in electromagnetics, the point source response, or the equivalence of point source response, is a Green's function. Hence, we can say that, well, I can write my AX of R, an arbitrary solution, as minus mu over 4 pi, the convolution of the input source, which is this one over here, with the Green's function, which is this function over here. Okay, and if you write this convolution in full, it looks something like this. It looks very complicated, but it's actually not that complicated. It's actually not that complicated. And hence, you know how to solve these equations. Even though it is vector in nature, sometimes we call this the vector Poisson's equation. Okay, this equation is called the vector Poisson's equation. And we know how to solve for each component of that. And if you apply this repeatedly, then you can say that if A is a vector now, then you can write this as minus mu, or is it, sorry, there's no minus over there. Mu 4 pi, the convolution of the, okay, this sometimes is written as dv prime, of the vector source with the Green's function. Sorry, there's no 4 pi. In the previous one, I have put 4 pi too many. Okay, I don't need that. So convolution with the Green's function will give me something like this. Okay, so you can solve for your A in this manner using this convolution property and Green's function. Having found A, then you can find your B by just taking the curl of A. Okay, and of course you also have to impose the condition that the divergence of A equals 0. This is called the Coulomb's gauge, as I said before. This alone is not enough to solve this, and you have to impose this gauge as well. And you can show that the solution is not unique if you don't impose this gauge, because if this gauge is not imposed, then I can always find a new vector A prime that is different from the original vector by the gradient of psi. And then I can show that curl of A prime is curl of A, because curl of grad psi equal to 0. So A is not unique. It can be easily made not unique or non-unique. The only way to make it unique is to make Coulomb's gauge. Okay, so if you have Coulomb's gauge being imposed, that it means the divergence of A prime is divergence of A minus the Laplacian of psi. And if this is imposed to be 0, and you can show that if this is imposed to be 0, and if this is imposed to be 0 as well, then it most of the time imply that phi equal to 0. So Coulomb's gauge or Coulomb gauge will eliminate the ambiguity or the non-uniqueness in this problem. I kind of talk about this in more detail in the lecture notes, or I wouldn't belay the point here, but the important take-home message here is that you have to have Coulomb gauge imposed to get a unique solution. So I like to liken this to vector algebra to give you some insight. So if I have a vector A, and then if I just only define this cross product with the vector B to be equal to a vector C, that is essentially what we're doing in this equation over here. The vector A defined in this manner is not unique, because if you look at this carefully, this is known. Okay, and there are more than one way that this cross product will give you the same vector C, because if you have a vector A and then you have a vector D, you can divide A into a parallel component plus a perpendicular component to D. And you can easily see that the parallel component, if I were to do D cross A, then D cross A parallel, and then D cross A perp. And this is always 0 because this is the component of A that's parallel to D. And hence, when you stipulate this to be C, you can put any parallel component into A, and this equation will still be satisfied. So stipulating this equation alone is not enough. However, if you stipulate the parallel component of A as well, if you do this dot product, it will not pick up this component. It will say that this is equal to something. And if you stipulate to be 0, then what it says is that there's no A perp component left. You force A perp to be 0. And then A is unique. Okay, then A is unique in this manner. Okay, I hope I'm saying things right. Okay, so this is one way to guarantee uniqueness. Any questions so far? Okay, then having no questions on magnetostatics, I'd like to talk about boundary conditions next. Boundary conditions are very important in electromagnetics. And without them, we cannot solve many problems. We go back to electrostatics again. And then we say that if you have a static problem, you can reduce it to solving Poisson's equation, which would look something like this. Okay, so this is Poisson's equation. And in order to solve this equation, we have to have boundary conditions. And if you do magnetostatics, okay, then we have to solve, to begin with, first this equation, curl of A equal to J, and we did some simplification for the homogeneous medium case. Then only we could solve this equation. But let's just look at the very simple case where we have epsilon that is a function of, say, x. Okay, so if we were to look at epsilon as a function of x, then let's assume that it's a very simple function. A constant is too simple, it's too trivial. So let's define a function with a step discontinuity. Okay, with a step discontinuity at x0. Then I rewrite my Poisson's equation in 1D. And if I were to rewrite this equation in 1D, del would be just partial x. And if I rewrite this equation in one dimension, it will be partial x, epsilon x, partial x, phi of x is equal to minus rho of x. So this is Poisson's equation for an inhomogeneous medium in one dimension. And I'd like to find out how I can solve this equation with the boundary conditions that are needed. Okay, so let me assume that rho of x is a sheet charge. So it will consist of amplitude rho of s, and then the delta function at x is equal to 0. So let's assume that there is a charge distribution rho of x that looks something like that. It is 0 everywhere else, but it has a delta function singularity at the point x0. Okay, so if you look at this equation again that we have previously, let me look at this equation again. So if I write Poisson's equation in one dimension, is equal to rho of s delta x minus x0. You can actually infer a lot of things about this equation already. That is that if I were to be outside the source region, if x is not equal to x0, the right-hand side is equal to 0. I have this equation to think about. And this equation tells me that whatever I have on the left-hand side, the derivatives that I have will make it go to 0. So one of the things that you can immediately conclude is that this has to be smooth. It cannot be discontinuous. You have to remember the notion that you learned as an undergraduate, which is that if I have a constant, the derivative is 0, but if I have constant with the ramp function, the derivative will give me 0 plus a constant. And if I have this function, and if I take its derivative again, I will get an impulse. This is something that we learn as electrical engineers, but we learn these concepts in the time domain as well. But they can be applied in the space domain as well. Okay, so I can just look at this equation and know that in order for the first derivative of any function to be 0, it has to be sufficiently smooth. And also, if this is a smooth function, it says that phi x has to be smooth. So these are kind of the intuition that you can gather by just eyeballing the equation. But then what we can do actually is to write this equation and integrate it, say, between x 9 minus delta to x naught plus delta. The source was located at x naught. Okay, we can integrate the first equation that we have written, and hence we can integrate this equation between x naught minus delta to x naught plus delta. And then if I integrate the right-hand side, and if the delta function is sitting right at the interface over here, I will pick up the value of the integral, and that we have learned as electrical engineers, and that would just give me minus rho s. Okay, I think I have a minus sign here, if I am correct. Because there's a minus sign in Poisson's equation, so I should have a minus sign here. Okay, so if you do this, then if you integrate this, then you will find that the integration can be done in closed form because this is an exact derivative. So I will have epsilon x d dx phi of x, and then evaluated at x naught minus delta, x naught plus delta must be a constant on the right-hand side. And what this says is that if I were to write this explicitly, using the fact that E x is minus partial x, phi of x, or just a simple derivative would be good enough, because I'm using the fact that E is minus grad phi, then this equation will become something like epsilon x Ex minus epsilon, let me see, I would call this x minus, or epsilon x plus Ex x plus, where x plus and x minus just refers to the value just next to the point x naught. Okay, if I look at the previous slide, and if I take the point x naught slightly to the right and to the left and call them x minus, okay, and x plus, then I would have this this boundary condition, and this would be equal to rho sub s. And this is the simple boundary condition that the normal flux, this is dx, x minus, minus dx, x plus, must be equal to the surface charge density. And this is probably something that you have learned before. in your undergraduate courses. Okay, but I'd like to introduce this concept as jump discontinuity induced by sources. If you have a delta function source, you can induce jump discontinuities in the normal component of the electric flux. And boundary conditions have a lot to do with the partial differential equation or the differential equation that you are operating with. And if you just eyeball the ordinary differential equation, you can infer different kinds of smoothness condition, that this has to be sufficiently smooth in order for this to go to 0. And this has to be sufficiently smooth in order for this not to have singularity. And if you have a singularity on the right-hand side, the only place where this singularity can come from is having to impose a jump discontinuity on this quantity over here, so that when you differentiate it once, you get the singularity on the right-hand side. That is essentially what is happening here. Okay, so let's go to other kinds of boundary conditions, like what we can infer from Faraday's law. Okay. Faraday's law is the statement that curl of E is minus dB dt. And that by just eyeballing this equation, you know that the right-hand side is finite. Because the right-hand side is finite, the left-hand side is actually a whole bunch of derivatives, because curl of E is actually equal to x partial x plus y partial y, ex and ey here. Let me put ex and ey here, cross with x ex plus y ey. So I'm going to write this in a way in terms of a local coordinate system. If I have an interface, I can always define a normal to the interface. That normal, I would call it the y hat in the local coordinate system. Then I will have a tangential component t hat, and that I will call it x hat in the local coordinate system. And then there should be the y hat coming up. Sorry, a z hat coming up of the paper somewhere, x, y, z. Okay, so I can write this curl operator in the local coordinate system. And if I go and work this out using the distributive law of cross product, then what I have on the right-hand side of this equation can be simplified. And then I would have this, I should have 4 terms. Okay, because there are 4 terms, but some of the cross products are equal to 0. Let me see, let me go this, get this to go away. And then I would have the right-hand side being equal to z hat partial x ey minus y hat partial x ez. Okay, if you take this cross products and assuming that some of them are going to 0, then I would have only this thing. And if I take into account of the other terms as well, okay, it turns out that I will have a z hat term coming from partial y ex, and then I will have an x hat term coming from partial y ez. Okay, and if I look at this thing, and if y is actually in this direction, y is in this direction, and that because the right-hand side is finite, and that the right-hand side is finite, this has to be sufficiently smooth. This has to be sufficiently smooth so that when you differentiate it with respect to y, it does not produce a singularity. So if I just eyeball this equation, that if curl of E has to be finite. And then across the interface, this has to be finite. Has to be finite. Then it says that EX and EZ have to be smooth enough so that differentiation of them in the y direction does not produce a singularity, because I don't have a singularity on the right hand side. And then if you think about this, EX and EZ are tangential components of the electric field. And finally, what it amounts to is saying that if I call this region 1 and this region 2, it says that E1 tangential, E1x is equal to E2x. That's what it means here. And then E1y z is equal to E2z. Okay, this 2 has to be true. Otherwise, you will have a discontinuity that when you differentiate it, you will get a singularity, which is not right if you just look at this equation. So this can also be written more compactly by saying that n cross E1 is equal to n cross E2, where n is just a unit normal to the interface. And we will take the cross product of an electric field with n, it will pick out the tangential component. You can convince yourself of that quite easily. And hence you have the fact that tangential E is continuous from Faraday's law. And this usually is proved in a different manner in many textbooks, but in this course, I like to use physical argument that you can just look at this equation as a partial differential equation. You can eyeball immediately that tangential E is continuous. Okay, then we can look at Gauss law. And if you look at Gauss's law, what we have is that divergence of D is equal to rho. And again, you can write this Gauss's law in the local coordinate system, where you have a normal pointing in this direction, and they can call that normal to be the z coordinates, and then they can have a tangential component. T1 is equal to x hat, and then they can have T2 is equal to y hat. I can put a local coordinate system to that. And then they can write divergence of D using this local coordinate system. Then it will be partial x dx plus partial y dy plus partial z dz. If I express this in Cartesian coordinate, and if I express this in Cartesian coordinates. And then if there is no charge on the right-hand side, all these derivatives has to be finite, which means that this field will have to be sufficiently smooth in order for divergence of D to be finite. However, if rho is a surface charge density, let's say in terms of the local coordinate system, if I write in terms of the local coordinate system, the charge density has a delta function singularity. Okay, and if you eyeball this, and if you have this to be written as rho s delta z, the only term that can produce a delta function singularity is this term here, which is the derivative with respect to z. All these are derivative with respect to y and derivative with respect to x. They cannot produce this singularity. And this is the expression of a surface charge singularity residing at the interface between two media. And these two media can be like media 2 and media 1, and so on. And then if you do that, then you can prove that the z must be continuous, and that if you were to look at the z at z, equal to 0 plus minus dz at z equal 0 minus at an interface, it must be equal to the magnitude of this charge singularity that you have. This is just by singularity matching. And you can rewrite this as being that the normal component of the fluxes is equal to the surface charge singularity. And hence you can just eyeball these equations and come up with the continuity equations for the fields. And you can do the same thing to Faraday's law. Or not Faraday's law, Ampere's law. Okay, you have Ampere's law being divergence of J equal to J plus partial D partial T, and this is Ampere's law. Again, if the right-hand side is finite, it will impose a certain kind of continuity condition on the magnetic field from the viewpoint of a derivative operator. However, you can show that if J is a current sheet, okay, residing at the interface, and let's call this having a Z coordinate, something like this, then you can show that by matching singularity again, that the discontinuity in the magnetic field must be equal to JS. Okay, and this is a boundary condition for Ampere's law. And in Gauss law, of course, you have divergence of B equal to 0. And from this, you can easily deduce that n dot B1 minus B2 must be equal to 0. Okay, so Ampere's law induces this boundary condition. Gauss law induces this boundary condition. And then we have Gauss law for electric flux inducing this boundary condition. And then we have Faraday's law inducing this boundary condition. So all the boundary conditions are derivable from the 4 Maxwell's equations. They are all buried in there. And you have to look at these equations and derive or gain an intuitive feeling as to why they impose a certain kind of boundary conditions on the field. I'll stop here since my time is up. Are there any questions? I think somebody asked me about how to hand in homework. I will ask the TA to email you the procedure on how to do that. I think Ivan Omatowski should at least know how to do this. Okay, I'll stop here and we can reconvene again on Friday. Okay, I'll talk to you later and keep safe. The epidemic is still raging out there, and hopefully things will become better with time. Okay, thank you very much.
Thank you.
Thank you.